Welcome back for the afternoon session. We're going to cover Spark, Shark, and some machine learning, the beginning of the machine learning during this session before the coffee break. A couple of quick announcements. Amazon, one of the lab's sponsors, is hosting a reInvent conference that you are all welcome to. Slightly pricier than the AMP Camp for those of you that registered to come in person. Though you can get you can mention AMP Camp and get some dollars off. So you need to email Simone at Amazon.com if you're interested in attending this with the AMP Camp discount. Before we start, a quick comment to the people who are watching on streaming about the exercises. We will be publishing the exercises on the website under this, ampcamp.berkeley.edu/exercises shortly before the exercise session starts, which is at 4:15. For those of you who are here in person, we will give you more instructions about how you'll actually receive the host name that you can SSH into and the instructions for you closer to the time of the exercises. So now I'm going to give it over to Reynold Xin, who will talk about Shark. Reynold's a third-year grad student, PhD student in the AMP lab, working with Mike Franklin, primarily on database-related things. And he's been working really hard on the Shark project to grow a community of active users. And I'll let Reynold tell you the rest.
Hear me okay? Thanks, Andy. So I'm going to talk to you a little bit about Shark. But before I actually start, we just saw this blog post on O'Reilly, which is pretty cool. I just want to share with you. Fan, who might be sitting here, who actually has a Twitter handle at Big Data, which is really hard to get, I presume, with all the buzz going on right now with Big Data. Wrote his blog post, presumably while he was here. It's pretty cool. Just want to share with you. All right, let's get started for real. So I want to talk to you about Shark, which, if this is the first time you're hearing about this, Shark actually comes from the name. You take the Hive, the H from Hive, and replace with the P in Spark, it becomes Shark. So first of all, I want you to stare for 30 seconds maybe on this on-screen MapReduce program. This is MapReduce pseudocode, which wouldn't even compile. It doesn't really satisfy any language syntax. But conceptually, some pseudocode that does something. Try to look at it, see if you understand it for 30 seconds. OK. Put up your hands if you understand what it's doing. All right, it's probably about less than half of the people. Now let's take a look at this, a SQL query. And look at it for maybe 20 seconds. Or maybe not even 20. Put up your hands if you know what it's doing. All right, majority of people put up their hands. So what it's doing is really assuming we have say, a table with two columns, page name and page views. And we're trying to grouping by the page name and then take the top pages with the most hits out of my table. So let's go back into a MapReduce program. This is actually conceptual pseudocode, which is much harder to understand. And this is actually a fairly simple query. You could write it with a few more subqueries and make a lot more MapReduce stages and make it ridiculously hard to actually understand and maybe much harder to write. How many of you are confident you can write this SQL query in, say, 5 minutes? Just put up your hands. All right, most of you. How many do you think you can write this that actually compiles and runs on Hadoop or Spark after Mate's?
I think on the left side, instead of sound, it should be right.
Yeah. See, I can't even get it right. And I've been working on this for a long time. So how many of you are confident you can write this that compiles and runs on Hadoop? Or you can write a Spark similar program in 5 minutes? A couple people put up their hands. So keep that in mind, and we continue with our talk. So the talk today, I'm going to focus on mainly a couple of things. One is I'm going to give a high-level introduction of Apache Hive and Shark and why we built Shark. And then I'll move on to talk about the data model and query language in Hive with Shark shares. And I'll give you a demo on Shark. We're going to be, I don't think it makes a lot of sense for me to actually teach you SQL. So I'll just be running some demos to show you how Shark is actually running on EC2. And last but not least, I'll give you a couple more advanced things that talk about so the performance tuning and improvements we have done to Shark is beyond the simple SQLs. First of all, Hive. So bear with me if you already used Hive before. Hive is initially developed by Facebook that essentially puts a structural schema onto HDFS data. And it compiles a HiveQL query, which is a special flavor of SQL, into MapReduce jobs. It's widely popular. 90%, I believe, 90% of the Facebook Hadoop jobs are actually launched by Hive. And it's since then being open source Apache top-level project. So it's kind of ironic that Hadoop being one of the most canonical examples of NoSQL movement, most of the Hadoop jobs are actually generated by end users writing SQL. And it is very important, for those of you who are less familiar with databases, it's very important to actually differentiate two terms, which one is OLTP, OLAP, the other one is OLAP and OLTP. OLTP means online transaction processing, which imagine if you have a website, the OLTP database is really the one that's serving the data to the end user, and you have very stringent latency requirements. Versus OLAP has a much different focus. Or throughout this talk, I'm going to use the name data warehouse synonymously with online analytical processing, or OLAP. For all practical purposes, they are really the same here. And OLAP focuses on scalability and extensibility, which is Hive primarily designed for. It's not designed for running low latency queries that get very small amount of data. Rather, it's designed for handling a very large amount of data in batch. So let's expand a little bit on scalability and extensibility. So Hive runs as a client library through MapReduce and compiles queries into MapReduce, which runs on Hadoop MapReduce, meaning it's fault tolerant and massively scale out on commodity hardware. Makes it very different from traditional data warehousing coming from relational databases. It can handle petabytes of data at ease and much easier to provision than traditional data warehouses. So think about if you've ever conducted a project on data warehouses, enterprise data warehouses, it takes months to years to actually provision, to do the planning, and then to set it up, purchase the hardware and the software, setting up, making it running. In the case of sort of Hive world, you basically set up a Hadoop cluster, start dumping data in, and when you run out of capacity, you just keep adding more nodes to it. The other part it focuses on is trying to be very, very flexible and extensible, because it's initially developed by Facebook to accommodate the needs of data analytics at Facebook, where data are highly nested. So Hive, the first thing Hive does is make the data type very flexible. There's primitives and complex types, and very good support for nested data. And then the next thing is SQLs are rigid, and we need sometimes more complicated analysis. So let's let the user-defined UDFs and UDAFs, user-defined functions or user-defined aggregate functions, really easily. And let's take it one step further. We even allow the user to actually write scripts, and we can launch those scripts as MapReduce jobs through pipes and combine them with SQL. And then the serializer, deserializer, which really transforms the input data into the structure format the Hive can understand. So you can use serializer, you can write serializer, deserializer yourself. Hive by default comes with the one for text, for binary sequence files, for JSON, and you can use it for, say, protobuf, thrift, and Apache Avro. And it's compatible with MapReduce API because it runs on Hadoop MapReduce. And so, for example, you can read data from HDFS, HBase, Amazon S3, variety of other formats. So take a look at the architecture. Again, it comes as a client-side library to the Hadoop MapReduce. And there's a concept of metastore, which is really what you typically call a system catalog in a traditional relational database. And the system catalog, or the metastore, runs a standalone relational database by itself and tracks all the metadata of your data. So all the table information and schema information are contained in metastore. You could run it as an embedded Apache Derby, or you could run a MySQL cluster for better availability or other relational databases. And there's a command line interface to Hive, as well as a JDBC interface that can connect to a Hive server, which is all powered by a driver. And the driver itself, when you supply it with a relational query or a HiveQL query, it goes through a similar process, a relational database, where we start by parsing the query, generates an abstract syntax tree, and turn the abstract syntax tree into a query plan. And then the query optimizer will apply optimizations to turn the query plan actually into a physical query plan that's sent to the Hadoop MapReduce for execution. So all the execution itself runs in Hadoop MapReduce. And most of Hadoop MapReduce programs are IO-bound, and so is Hive query processing. So you all heard about the Spark talk earlier. And the question we had in mind last year was, can in-memory computation actually help in the case of Hive, where people have petabyte-scale data warehouses? How do you fit a petabyte into memory? Would it even worth it? So I'm going to break all my academic integrity by citing a tweet I saw yesterday. Medium Hadoop input job size at Microsoft, Yahoo, and Facebook is really only 15 gigabyte, even though everyone claims they have petabyte warehouses. The HDFS cluster probably actually have petabytes of data, but most of the query they run don't run on the petabyte warehouse itself. They run probably focused on very small working set of windows, say your visit logs from yesterday, or in the more sort of traditional OLAP style queries, you have a huge fact table and a bunch of very small dimension tables. So data warehouses actually exhibit very strong temporal locality, meaning, and also spatial locality. The same data can be repeatedly accessed. In the case of, say, an OLAP report, you might have 100 queries that are running, scanning through the same data again and again and again. And if we can cache those data in memory across the cluster and use those memory to answer queries, we can obtain order of magnitude or maybe even higher throughput than reading from HDFS every time. So the question we ask is, Hive is flexible, Hive is really nice. Can we retain all the benefits and exploit the temporal locality by using Spark? So we took a deep look into the Hive architecture again, and we swap out the physical plan generation and execution engine and adding a cache manager with some tweaks to the query optimizer, and essentially turn into Shark, which compiles HiveQL queries using the Hive parser and generate a physical query plan that actually runs on Spark. So Shark is a data warehouse system that's designed to be compatible with Hive, which means it supports HiveQL, supports Hive UDFs, serializer, deserializer, Hive scripts, and Hive data types without modification. There's some features we don't support, and I will mention some of them in the talk. It aims to make Hive queries run faster through a number of means. One is caching data in memory, so you can obtain much higher throughput. And the other one is we have done a lot of other optimizations throughout the query execution process to actually improve the performance. And last but not least, since we built it on top of Spark, we actually took one step further and make it integrate really well with Spark. So it's a Shark shell or a Shark Scala API where that allows you to actually return, instead of running the query, returning the result, it runs the query and returns an RDD itself, and you can perform further transformation on RDD. I'll talk a little bit about it at the very end. So again, the most important thing for Shark in comparison with Hive is probably just caching data in memory across a cluster. And this is done through just the create table statement, where you can say create table. If you supply with a table name that ends with underscore cached, you actually cache it in memory. So it's a binary flag. And you can supply what data you want to cache by stating it in the SQL select statement. So in this case, I'm just saying get me everything that has a count bigger than 10 and cache it in memory. And once you created this cache table in memory across a cluster, you can use it to answer queries. There's no difference between query a regular table versus querying a cache table. So let's talk a little bit about data model. There's really 4 kind of concepts that are hierarchical in Hive, which Shark shares. I ignore the first one, is the databases, which really means a schema, depending on what world you come from. But forget about that one for now, and start with tables. A table is a unit of data with the same schema, which means all the data in the same table have the same columns. And then within the table, you can create partitions. So this is say, for example, if you have data that are indexed by, or if you have log data, you can partition the data by date. And Hive uses this partition information to actually prune the data before launching the MapReduce jobs. So 2 ways to do filtering in sort of Hive. One is you actually filter in your mappers. And this is slow. The other one is you just don't include those data if you know you wouldn't need it to actually answer a query. So the partition data is actually maintained in the meta store. And when Hive is generating a query plan, you do the pruning before sending it to Hadoop MapReduce. And there's buckets, which provides an extra level of pruning. It's a hash partitioning within partitions. And it's right now, Shark actually doesn't support it yet. And then let's go about data types. So 2 types of data types, again, in Hive. There's primitive types, which are ints, booleans, floating point numbers, and strings. This is very similar to a typical SQL standard. And there's complex types, which makes it more interesting. You can have a struct, you can have arrays. I think arrays might be typical in relational databases, but certainly not structs and maps. Maps allows you to do sort of key value pairs of data. And structs is essentially similar to a C struct or Java classes.
Sorry.
Yeah.
Do those arrays have to be all of the same primitive type, or can you mix types in between those?
It's a good question. Actually, the question was, do the arrays need to be all of the same primitive types? It's a good question. I actually don't know a good answer on top of it. I've written a lot of test scripts, but I never actually do it. Does anyone here know that heavy Hive users?
You can mix.
My guess, yeah. So the answer from audience, you can't mix the types. And there's Hive2L, which is an intersecting subset of SQL. This a subset of SQL that includes a typical projection, selection, group by aggregations, sort, order, and joins, and subqueries, and unions. But there's a few Hive-specific extensions, including the transform clause, which allows you to launch MapReduce scripts through sort of Linux pipes. And then there's a variety of hints for performance optimizations, which are pretty well documented on the Hive website. So instead of actually teaching you SQL, I'm just going to run some queries on a cluster I just started up. And let's see if the internet works. Yeah.
Yeah, so you were talking about how Shark is sitting on top of Hive and stuff like this. So if you don't mind to get into a little bit of specific details, are you guys using the same engine and just building on top of it, or is it some kind of MLP notifications in runtime?
Yeah. So Hive comes in the, yeah. So the question is, we talk about we actually build Shark on top of Hive. What exactly does that entail? So essentially, we take Hive as a third-party library. And then we overrode, so the driver is a big starting point of everything in Hive. And we took the driver, we overrode that class, and we re-implemented sort of the run function in Hive. And then the run function actually launches the Hive parser, basically just embedded as a third-party library. And then everything else.
So basically, if we take a look into the Hive, sorry about getting into too much of details. If you look into the Hive implementation, so how the Hive execution is done is really a foolish way of just running a external Java process, basically,
Yeah, so the question is much longer than my answer going to be. The question was, so Hive runs as sort of a, Hive does MapReduce execution as a third-party library and generates sort of MapReduce programs.
And then it runs Hadoop.
And runs on Hadoop, yeah. And what this Shark just sort of generates a data flow for Spark and runs it.
No, basically my question was if you execute Shark instead of executing Hadoop jar from Hive. So what is kind of Shark way of doing the execution? Is it like Spark?
It launches Spark jobs. It basically launches Spark job. We embed a Spark in Shark, and then it submits sort of tasks to Mesos, or in the future, Hadoop Next Gen.
So basically, Hive remains the same, and it is being single user as before, and then it being the library to the cluster.
Exactly. And we also support the Hive server mode, which is the same thing as Hive. All right. Let's see. Actually, let me mirror my display. Is this big enough? Okay, so I have an Amazon EC2 cluster I launched before coming to the talk. It's about 20 nodes, and while I loaded the Wikipedia traffic statistics data you're going to be using for your exercises onto the cluster. And let's just take a look. So basically the data, I'm just going to make it bigger. The data are located in the HDFS/wiki/page counts. If we do just an LS, it's showing you 74 items, most of them about 200, 300 megabyte range. And the two of them, they're empty. We had used for just for checksumming purpose. We know we get all the data. And this is basically how you structure a Hive table. A Hive table is a directory on HDFS. And it contains all the data in the files within that directory. So basically, each of these files is part of the data I have. So 72 files times 300 megs, about 20 gigabyte range. And let's just take a look at one of the file. I'm going to cat the file itself.
Hey, Reynold, can you go one bigger?
Big enough. I could go one more.
For the streaming people.
Yeah. All right. So hopefully that's big enough. So I'm just going to cat one of the file to show you what's in the file. So as you can see, for each of the file, there's sort of a date string that concatenated with a time. So this is 2009, May 7th, 4 o'clock, probably GMT. And then the second field is called Wikipedia project code, which contains various information such as the language. So EN would be a page, an English page. And then the third column is a title of the page. And the fourth is the number of hits on that page in that specific hour. And the fifth is the size of the page. So this is just the data we got from Amazon Wikipedia traffic statistic public data set. So now let's switch to Shark. So I'm going to launch the Shark console, which is, actually, if this is the first time you see the MI, it's basically a bunch of folders in it. You're going to get the same instances when you're doing your exercises. Spark folder is a Shark folder. And we can launch the Shark console with just Shark bin Shark wizinfo. The wizinfo meaning I'm going to printing more logs, so I can actually walk you through the progress here. It's going to be very chatty. So this gives you the Shark console, and we actually built a toggle into Shark for you to actually switch directly between Shark and Hive. So you can do shark.exec.mode equals Hive, and it's going to change the prompt to Hive, and every query you run here is going to run through the Hive MapReduce. And if you set it back to Shark, you'll be running Shark. The first thing we're going to do is let's create a table. It's actually very long. So before you can run any queries, you actually need to put the schema onto the data itself. And the way you do is by create a table. There's two kinds of tables in Hive. There's external table and sort of internal tables. Internal table are the tables that are created by Hive itself. So the data are created by Hive. And the external table is for the data you already have on HDFS. So in this case, I preloaded the data, I copied it from Amazon S3 bucket onto HDFS, and it's already residing in the /wiki/page counts. And when you're creating the table, this is very similar to sort of traditional SQL DDL. Specify the finite number of fields and the name and the data types. And you can specify the row format, which by default assumes a text file. And then it's delimited by a space that I specify here, along with the HDFS location of the file. So I'm going to create it. I believe I already have the table created, so it's going to show me an error. Yes. So the table is already created, already exists exception, but that's fine. And once you create a table, you can do show tables to actually see what tables you have. So we have a wiki stats table in here. And you can do the normal describe that shows you information about the table. When you do a describe, it's going to show you the schema here, which is not very helpful if you just know the schema. There's another flag called describe extended, and then it's going to show you more information, including, in addition to the schema, it's going to show you a bunch of other information. There's more detailed information about the fields themselves, and there's information on the location of the files, which is on HDFS/wiki/page counts. And there's an input format, which in this case a text input format. And then the serializer, deserializer, again, that's the one that actually transform the unstructured data into structured data that Hive can understand. So the first thing I'm going to do is this query. This data is actually about 20 gigabytes, not significantly huge, but we don't have that many nodes. Serving from this all the time is going to be slow. I'm just going to create a cache table so we can load it from it. So as you can see, what I ran was create table wikistats _ cache select star. I'm basically caching the entire wikistats input onto a in-memory cache table. And then you see a bunch of, it's a very chatty log, but you see kind of what's going on. It's parsing it, but the more important, you see Spark is actually starting the tasks on the slave node. So basically when you type this query into the Hive command, or the Shark prompt, it's going through the driver and launching Spark tasks. And you see it's tasks starting, and you see it's saying there's 177 tasks, and they're running one by one. And at some point, you will see cache entry added. So it's basically adding the cache entries onto the slave nodes. And each of the slave nodes now has 9.3 gigabytes of memory left for caching. And then this time it's adding 143 megabytes of data. And you keep adding, and all right, it's finished in about 20 seconds. So let's just run some. When you do show tables, you see the wikistats cache table here. And let's run, say a count. We want to know how many records actually there are. So it's just counting. It's because the log is chatty, it makes it run a little bit slower because you have to transfer a log from things. So in about 5 seconds, I got was that 300 million records in my wikistats data. So let's running a count. Let's run. So my wikistats have the first field is date time, right? I don't actually know at this point what's the range of dates and times in this data set. Let's just do a distinct date on the date time to see how many different dates and times are there. It's going to be running. And then let's go up. So it starts from 2009, May 6. I actually didn't sort it. Probably better if I sort it. But as you can see, it covers May 6, May 7, and May 5th. So it's actually covering 3 days and all 24 hours. Now, let's pick a random day 2009 May 7th and the second hour. Let's see what's the total number of hits on Wikipedia at that specific hour. So this is a simple aggregation. I'm just going to do page views from try this. Right, fairly quickly, about 2-3 seconds, you get the answer back. It's about 14 million hits in total on Wikipedia in that hour, 2009 May 7th. Yes.
So we have a pretty existing heavy investment in Hive, like tons of tables and stuff like that, and pretty like millions of rows and stuff. So do I need to do that cache thing of select, like create new table bias, select star from something for each of the hundreds of tables? Like how do I port my stuff to, let's say, sharp?
So if you don't create this cache table, the question, yes, thanks, Sandy. The question is, if I already have a lot of Hive tables, how do I actually use Shark to take advantage of the caching? Do I need to create tables, create new tables to actually use this? The answer is, at this point, yes. You would have to create the table. So you can query your existing Hive tables, but you wouldn't actually use the in-memory cache RDD to use it at this point. Yeah, it's limited by the aggregated memory in a cluster. And it wouldn't just blow up if you put more data into it. You have an eviction policy at the RDD level. Yeah.
So when you create a cache table, is the data cached at the time when you create the table, or is it again lazy caching?
Yeah, at this point it's actually created. The question is, when you create a cache table, is the table cached or materialized in the cluster's memory immediately, or is it lazily sort of materialized? The answer is, it is actually materialized immediately, although it's a one line of code to change that. Unlike Spark, we actually added a line of code to force that, so we get more predictable behavior. It's literally one line of code we can remove or add. Maybe we can add a switch to it. But good question.
And if I query a selected partition, a particular partition, and if it sits on, say, a few of the nodes, will it only use the data from that partition and then return the results, or will it still scan the entire memory space?
Are you talking about the Hive partitions or talking about the Spark partitions? Partition in terms of it.
Spark partition, data cached in memory.
Yeah.
And stored in partitions, right? And a cache table in Spark. And if I run the query, which is like the example that you just ran, if it is only querying a particular partition, will it scan the entire data set on all the nodes, or will it still use the partition?
So there's actually no index structure here to tell you that you don't have to scan a partition. There's just no information there. Although it's presumably something we could think about and try to build it. But you actually require to scanning through all the data. But scanning through all the data in memory is actually extremely fast. Yeah. Yes.
Let's switch to using a microphone because it's just.
Yes. Thanks, Andy.
If you have new partition data, do you have to recreate the cache table?
Yes, at the point.
Okay.
Yes. Presumably, you can do union, so if you want. So you don't necessarily have to recreate the whole table. Maybe I'll take more questions at the end, so I can actually run through with the demo.
Very quick, short one. What version of Hive are you using?
Right now it's with 0.7. We are updating it to 0.9, which will be released together with the next version release, coming soon. Yeah. So the question was, what version of Hive is this build based on? Yeah. So let's run. I think Matei showed you this Spark query that grabs for Berkeley in Wikipedia. Just for the sake of it, I'm going to do the same thing in SQL. So let's just select the page name, and then I'm going to sum up the page views. And so let's grab Berkeley in the page name, and then group by the page name itself. then order by the hits on the page, and then just take the top 10. So I don't want to find the top 10 pages on Wikipedia that's Berkeley on it. Just going to run that. And here you go. So UC Berkeley, as expected, has 383 hits in that 3 days on Wikipedia. And then there's a bunch of Wells Fargo Bank, Berkeley gets pretty good. I guess they have done a good marketing. So that's it for the demo. And so it's going to cover a little bit more about the SQL, the advanced stuff beyond just simple SQL, because you don't come here to actually learn SQL. Let's talk a little bit about how the query is actually executed. Think about this query. The page name, the one I just run. I'm finding all the top hits related to Berkeley on Wikipedia. How does this actually run? So conceptually, the 3 stages to this query, I took out the limit 10, other than everything else the same. Conceptually, there's 3 stages. The filter stage, which filters out everything that doesn't contain the name Berkeley, which is completely map only. And it's a group by stage, which groups everything by the page name. And the group by itself involves a shuffle. And then there's a sort stage. So we have to sort based on the output of the group by and aggregation. The group by aggregation itself sums up the total number of hits on each of the pages. And then it's piped into a sort. So in Hive, this is actually executed at 2 separate MapReduce jobs, or in the more Hive term, MapReduce stages. The first stage, they would pipeline the map and the shuffle and the group by into one map shuffle reduce. So you're reading all the data from disk. You does the filtering as a map, and then you do a shuffle, and then you do the aggregation as the on the reducers, and then you write the intermediate output, which is the aggregation output, onto disk, HDFS in this case. And then in stage 1, or the second stage, you read the intermediate output from disk, or HDFS, and then use a shuffle to sort the data. And then, after you sort, output the data back in. In the case of Shark, since Spark actually has the concept of a DAG, which direct acyclic graph, it's a representative of a workflow that's happening here. Again, it's very similar, that the map and the first group by is actually pipelined. And then on the same node, it's basically just reading data from memory, or if the data was never materialized in memory, reading from disk in this case. And then it's going to do a shuffle, everything, and then the output of the shuffle remains in memory. And then you do the second shuffle, which arrange. So the first shuffle is actually hash-based shuffle in Spark, because there's no need. We don't actually need the data to be sorted by page name. We actually need the data to be sorted by hits. So the first shuffle itself does a hash-based shuffle. And then the data stays in memory. And the second shuffle would be a range. It does a range partitioning. And then on each of the partitions, it's going to sort the data. And then you have a total order of things. If you add a limit clause like the one we ran, you actually don't need to, you can avoid the second shuffle by just taking the top K or top 10 on each of the partition. So you can get rid of the second shuffle. And this would be basically a sort of a maps arrow. And every mapper node just takes the top 10, and then you aggregate to take the top 10.
Just a quick question.
Yeah.
That is no different between Hive and Shark.
The question is, there's no difference here between Hive and Shark. The optimization here, I think the way the limit push downs are implemented is a little bit different. We have one that's slightly more optimized. I'll show you some numbers very soon. So just some performance improvement in addition. So just to highlight here, a lot of things, when we're running Hive or MapReduce, again, a lot of the intermediate data are going through disk, which makes it much slower, especially most queries that typically consist of multiple stages of MapReduce jobs. Whereas in Spark and Shark, it's really running as the same DAG, and there's very few I/O hits. And in addition to just caching data in memory and avoiding the intermediate data going to disk. There's a number of other things that just improve the performance. For example, I already mentioned hash-based shuffle and then distributed sort, and then just better push downs of limits. But just show you a couple charts on performance. So in this graph is some query ran before as well, maybe 70 gigabytes of data on a 10-node EC2 node. And you run a query in Hive, it takes about 38 seconds to actually process the data, a simple grep query. And then in Shark, it takes about only 11 seconds. A lot of this actually goes to sort of Hadoop MapReduce overhead. It's much less about, the real processing time for Hive here is probably about 11 seconds too, except the scheduling, other kinds of overhead, it makes it push up to 38 seconds. But as soon as you start caching data in memory, you can sort of get an order of magnitude lower latency by loading data from memory. And then to illustrate some other things that's unrelated to caching, if you run sort of a very heavy group by query here, because this is a table, sort of a table is this. So in this specific table, the number of distinct IP addresses is huge. So this group by cost is actually very, very expensive. And the hash-based aggregation and the limit pushdowns we have done actually makes Shark's performance much better, even for running on this data. So this is a 200-second difference. It's not just because of scheduling. It's no way scheduling actually accounts for 200 seconds. So I'm actually running out of time soon. So I'm going to go quickly through this two performance tuning parameters that are very important to or very sensitive to how Shark and potentially Hive will run. And one is setting a number of reducers. The other one is map site aggregation. So going back to this graph, in Shark, which actually runs on Spark, Mate probably already mentioned that you have to set the number of reducers for Shark to actually assign an appropriate number of reducers. And the reducers are used to actually do the shuffle. You can set it with the Hive command set MapReduce.reduce.task equals some number. And Shark will read it from the MapReduce Hadoop environmental variable. And then for the mappers, it relies on Spark to actually infer the number of mappers you need. So you automatically launch a right number of tasks. But for reducers, you actually do have to specify it. And each of the reducers is responsible for one partition after the shuffle stage. If you have too few number of reducers, let's say if you have a terabyte of data, and you only have 2 reducers, each reducer will be sorting half a terabyte of data. And the sorting at this point is actually internal source, no external sorting or per node. And you actually get an out-of-memory error. The sum works on going to, there's a pull request right now on doing external sort for Spark. But even with external sort, setting the right amount of parallelism is very important for performance. And the other fairly important thing is map site aggregation. You can set sort of a Hive environmental variable, which is hive.map.aggregate equals true, and you turn on map site aggregation. What does it mean? So aggregation functions, most of them are commutative. Let's say if you take max, if you want to compute sum, it doesn't matter the order of them that's being performed. And if on each of the mapper, there's 2 ways to execute a query. Say, I want to count my page hits by date. 2 ways to execute it. One is I push all the data to a reducer to do the sum. The other one is to actually execute the sum on each of the mapper. So the mapper will build a hash table for each of the unique key on its partition, and then pre-process it to do a first-level aggregation and to reduce the amount of data shuffled. But this mapper, to build a hash table can be expensive because your hash table entries equal the number of keys, distinct keys you have on each of the map partition. So let's think about 2 queries. One is on the same Wikipedia data set. I select the date and I sum up sort of a histogram of hits on the date. And the other one is I sum up the hits based on the page name. In the first one, there's very few distinct number of dates because there's only so many, we only have 3 days of data. Even if you have a whole year of data, there's only 65 times 24. It's a very small number. Versus Wikipedia has 100 million pages, distinct pages. So on each of the partitions, there's probably in the order of tens of millions of distinct page names. And building a hash table for tens of millions of distinct page names is very expensive. So you would want to turn map site aggregation on when you have small number of distinct keys, and turn it off when there's a large number of distinct keys. And there's a lot of things is the SQL Spark integration. So since Shark actually runs queries in Spark, we thought it would be nice if we can actually integrate Spark programs into Shark programs. It's really easy to select data from SQL and doing simple aggregations. So why don't we let the user, enable the users to do what SQL does best and what Spark does best, which is more complicated iterative computations. So we implemented an API called SQL to RDD, where you can actually invoke in Shark, and it will return you the result of the query as an RDD, which means it doesn't have to be materialized yet. It's basically representing RDD with a lineage tracing all the way back to the Hive queries. And then there's the normal Spark. You can do a map row, which is essentially the same as a map, except it's a few more primitive provided, so you can get the columns out structurally. And then you can run any kind of RDD transformation as you like in Spark itself. So you can push the simple selection into SQL and then run your, say, machine learning in Spark, which you'll learn about k-means in the next session when I'm gone. So quick note on how to get started. The Spark EC2 AMI right now, the latest AMI actually comes with Shark install. You can use the same script that launched Spark to launch Shark. And if you want to build it on deploy in your private cloud or data center, it requires Mesos at the moment. And the Hadoop next-gen deployment is coming soon. And today's exercise, you get each of you on site will get a 4-node EC2 instance preloaded with the Wikipedia traffic statistics data I just used in my demo. The streaming audience will get instructions on how to launch an AMI with an AMI ID. And you'll be using Shark and Spark to interact with the data. Thanks. I think I'm running out of time. Maybe you can take questions offline.
There's some short
I can
questions.
take a couple more questions while Ariel's setting up. Anyone?
Is there any significant performance improvement because you're using Mesos as opposed to Hadoop scheduling?
For very low latency queries, you're able to push sort of the latency to sub-seconds range by running on Mesos. If you put it on Hadoop, I think the scheduling overhead come down from maybe 20 seconds to 5 seconds now, but it's very hard to go below that if you run it on Hadoop. Although for next gen, since you can do a coarse-grained scheduling, you can keep the slaves alive, and the second level scheduler provided by Spark and Shark is actually doing the scheduling. So the overhead there can be very low too.
All right, one more question.
I know that you guys have been working a lot with AWS. Is there any particular sort of cluster configuration that you guys would recommend? For example, do you push the high memory instances for Spark implementations? Do you see one extra large? Or do you have any comments on that?
So this depends highly on your workload and the amount of data you have to shuffle. I think there's a few things you need to keep in mind. One is, so what's your shuffling pattern? Because when a query is streaming from memory, there's two things that happen. One is become CPU bound. The other one is it becomes shuffle network bound. So if you shuffle if your typical query shuffle large amount of distinct keys, you probably want the one with better network performance, which is not always an option. It's more expensive. But the other thing is it really requires a lot of tuning to understand what's your workload characteristics. I typically, when I do experiments, launch with a double memory extra large, which gets me 30 gig of RAM, which is double the price of the one that give you half of the RAM. But consolidating into beefy nodes gets you better performance because you reduce the shuffle overhead.
Thanks again, Reynold.